Hello, welcome to another class of digital design with Verilog. Today class we will discuss about RTL design. Particularly we will discuss many examples, complete examples. So, including implementations and interfacing with outer world. So, particularly RTL designs with ASM with examples and detailed implementations. So, not Verilog implementation, but we will try to implement using standard logics. Okay. Outline of today class is ASM building boxes. What are the different boxes? Already we have discussed, do a recap. Then what is ASM block? Okay. So, ASM block it execute in one cycle, and what constitute of ASM block that we will see. Then complete design examples. So, we will do case study of two examples completely. So, one example is serial additions and another example is sum of first and odd number. These two examples we will look at very carefully, and in the designing process we do model the problem using ASM. So, FSM plus data path, then we go for data path generations, then FSM and data path connections also we looked at how we will interconnect, and then finally implementation of ASMs, and we looked at interfacing with external world, how the overall design will look like. So, reference material we have taken from two books, particularly Mano book and Kumar book, chapter 8 of Mano book, design at RTL level, and chapter 15 of Kumar book, A. Anand Kumar, fundamental of digital circuits, particularly algorithmic state machines chapter. Already discussed in earlier classes. So, what is ASM chart and what ASM chart constitute? It have three type of element or boxes. One is a state box, a decision box, and other thing is conditional output box or conditional box. This conditional box is actually it's help us to model the maritime machines. Then state box help us to model more type of machines, and decision box help us to think like doing the things in algorithmic flow way. So, this is the combinations, and these are the three building blocks or three type of element or boxes we use. Let us discuss what is ASM block. So, suppose we already design a ASM, then what is the ASM block? Okay. So, suppose this is the one example of one algorithmic state machines. Okay. This is for serial additions, whatever we are taking case study example, same example we have taken. Suppose this is the ASM of the problem, then what is ASM block? ASM block is an ASM block include a state and all its outgoing edges, condition boxes and conditional state boxes. So, clearly this red mark one. So, this one is red mark one. These are actually so one box. Okay. So, one block. So, state box, its associated condition and its associated conditional state boxes, state box, condition box and associated conditional box, state boxes. So, all three. Okay. So, it constitute a block and all part of an ASM block execute in one cycle. So, most importantly, so this execute whole things execute in one cycle and this whole thing execute in one cycle, and at what time it executes? It execute at the end of the cycle. So, the concept is at the end of the cycle this block executes, and a block execute in one cycle. Okay. So, whenever block is activated in the cycle, so this whole block get executed. So, not only the state box, not only the conditions, not the conditional state box, all the things get executed together in the cycle. And in this particular examples, we have two blocks. So, particularly these two are shown here, ASM block. This is one block and this is another block. So, state box and all its outgoing edges, particularly this is outgoing edges, this is outgoing edges and this is outgoing edges. All outgoing edges, condition box and conditional state box. So, all three things, state box, condition boxes, all outgoing edges of condition box and conditional state boxes, all execute in one cycles, and this constitute state, this constitute we call as block, ASM block. Okay. ASM block is include a state and in all its outgoing edges, condition boxes and conditional state boxes. And this is one another example. So, in this example, so this particular this example have three states, clearly state 1, state 2 and state 3. There are three states, and these states have associated, this state have associated what you can say, this is 1, this is 2 and 3. There are three states and this is associated condition box, this is associated conditional state box, this is associated conditional state box and this is again associated conditions. So, this whole red thing, it constitute of one ASM block. So, state and its associated condition box and conditional state box, conditional box. So, this whole things constitute one ASM block and it execute in one cycle. Okay. So, a ASM block may be much bigger than a simple state, and these are another block 2 and this is block 3, this one is block 1. So, this example of 3 block. So, ASM block, number of ASM block, it depend on number of state box available in the ASM. So, in the previous diagrams, previous ASM examples, so because the whole things execute in one cycle and whenever start is equal to 1 and Q0 is equal to 1. So, this is go to the in the next cycle it goes to the this small one. So, in this example, so what happening? So, this Q0 is 1 because Q0 is equal to 1 and start is equal to 1, start is equal to 1. So, look, the start is equal to 1 and Q0 is equal to 1. Whenever this start and Q0 is equal to 1 and it is in currently in this state, that means it goes to the transitions when start equal to 1 and Q0 is equal to 1, then that means it will follow this path and it will go to mul 1. So, the whole thing executes, the whole block executes in one cycle and it goes to the next cycle, because and in next cycle it reaches to the this block. So, exactly same thing, this is Q1 and this is start, and whenever both start and this thing 1, then it goes to the, this is currently in block 1 and it goes to the block 3 and block 3 is mul 1. So, block 3 is mul 1, this one is block 3, it goes to the block 3, the whole thing executes in one cycle. So, that is the beauty of ASM block. Okay. So, this is output appears while in the states and register transfer occur at the clock while executing the states, and new value occurs in the next state. So, new value occurs in the next state. So, this is the next state and new value occurs in the next states. So, this is the concept of ASM block. ASM block is state box and its associated condition box, all outgoing edges and conditional state box, conditional boxes. Okay. So, all three things constitute of a ASM block, and an ASM block execute in one cycle. So, let us look at concrete examples of digital design examples with ASM. An example is serial additions with only one full ladder. So, in the earlier classes we have already studied about the serial additions. In the serial additions it had two input x and y, and this is the full ladder. Okay, and it takes x and y input, it generates s and it generates c, and the same thing gets stored in a flip flop. This is a flip flop, and in the next cycle this whatever it stored next cycle, because it is D flip flop, next cycle it get used. Okay, so this is the serial additions, and what it do actually, it's do means suppose x0, x1, x2 up to xn, and suppose y0, y1, y2 up to yn, then it's actually add the values. This is s0, then it's generate a carry, then s1 it generate another carry. So, in this way it's proceeds. Okay, so this is the serial additions using only one full ladder, because at a one given instance only one bit is getting used. Okay, so only one full ladder is more than enough. So, we can do in serial additions. So, how the FSM will look like? So, this is Mealy finite state machine for binary adder. So, based on what are the value of E and means x and y. So, in this case there are two states. Okay, so, two state A and B, and what is the value of means two state A and B. So, what it says, this state says this is the what are the earlier carries. So, this states says about the carry bit. The state says about the carry bit. If carry bit is 0 and xy is equal to 0, xy is equal to 0 and output will be 0, carry bit is equal to suppose 0 1, this output is 1, okay, but again carry bit will be stay at 0. In this case input is equal to suppose 1 0 and carry bit is 0, then it will generate sum is equal to 1 and carry bit is equal to 0, and carry bit again carry bit represent the state in this case. Okay. So, whether bit will change or not. Suppose you are in state 0, carry bit is 0 and you got a 1 1, then result will be sum will be 0, this represent the sum, okay, and this represent the carry, state represent the carry, okay, and output represent the sum, okay, output represent the sum. So, this is the Mealy FSM of binary adder. So, if we convert this to FSM, so FSM how it look like? So, this has two states, so A and B, okay, so similar to the Mealy FSM, and this is the state A. So, in this case output this is what I can say, this one is carry bit, and based on the xy value of xy, if it is 0 then output also goes to 0, and if it is 0 1 and 1 0, then sum will be in this case output sum is equal to 1. So, whatever the this things it's shown is actually 0 1, this part is shown. So, this part is actually this part correspond to this thing, okay, this part correspond to this thing, and if this part suppose you are in state 0 and got a 1 1, and then you go to the next state, if this part this things is correspond to this one. So, every edges, so this part suppose you are in this part is corresponding to this one, this part is this is actually correspond to this part. So, this are actually other part is correspond to this one. So, similarly for state B also. So, based on the values, if it is 0 0 and 0 1, then it's go to the same state, 0 0 and 0 1, it goes to the same state, but sum is 0. So, this is the behavior of binary adder. So, this is the ASM diagrams. So, similar to we can correspondingly you can write draw the ASM diagrams. Once you draw the ASM, suppose from the ASM, so we want to generate circuits. So, this is kind of reverse engineering, but we want to do that thing. Okay. So, this represent the when sum is equal to 1 bit. Okay. So, if it is 0 0 and currently you are state in B, okay, and you got a 0 0, then in this case it will generate a sum 1. That 3 cases it is generating sum is equal to 1. And in this case same examples we are taking, and in this case there are 2 ASM block. Number of ASM block is same as number of states. Okay, in this case 2 states, okay, 1 and 2. For these 2 states we have 2 ASM blocks. So, an ASM block execute in one cycle. Okay, that means ASM block means the state box, associated condition box, and all its outgoing edges and conditional boxes. All three things get executed in one cycle. That means this whole block get executed in one cycle. Okay, and based on conditions it go to the next cycle, next what I can say ASM block, or it may stay in the same ASM block. And so, earlier we have already shown this diagrams, and this ASM have 2 blocks. Okay, and ASM block means include all a state, all its outgoing edges, condition boxes and conditional boxes, that we already have shown. And in this example there are 2 block. So, if you want to implement this ASM, suppose we want to implement this ASM. So, what will be the logic? So, clearly from the ASM design, so clearly how many states are there? 2 states. 2 states can be encoded into means in one flip flop, 2 states can be encoded into one flip flop. Okay. So, that is why we require a single one flip flop D flip flop to store the states. Okay. And for transitions, what is the output? Output is S. For what conditions output S will be 1, that we need to decide. And what are the state transitions? Okay. So, in this case this is next state logic. So, we are storing 0 or 1 in the D flip flop, this is the state informations, and from the states based on the input, okay. So, based on the input, so states, this is the state. So, next state logic, so next state is what? Function of current state plus input, same as FSM. Okay. So, this is same as FSM. So, here this is the next state logic based on value q and current input this. Okay. And Z logic, particularly output logic, this one is output logic, Z logic is output logic. So, we need to look at you are in which state. Based on T0, T1 there are 2 states, and this is kind of decoded. Okay, kind of decoded. So, this is if your q is equal to 0, then this will be enabled, if q is equal to 1, then this will be enabled. So, this is only the 1 cross 2 decoder is there. So, already decoded, and Z logic will be based on the decoded thing. So, you are in which state and how it will behave. So, suppose you are in T0 state, on what conditions S will be 1. Okay. So, that thing we will see. So, if you look at the things. So, this is the ASM for Melli FSM of binary adder, same thing, this is the ASM. So, this one is transitions. If you look at Q values, so you are in state, suppose first case you are in state 0, you are in state 0, you are in state 0. On what case you are getting a 1 values. So, this is this one is for next state 1. So, on what values you are going to the next state. Suppose you are in state this one, and what value of x y it tries to the next state. So, clearly, so if you are in state 0, only 1 will go to the next state, that means this line. So, we are in state A, okay, state 0, and if you are getting x y is equal to 1, then only it will go to the next state, and this correspond to yellow correspond to this one. So, this one, that is why this is correspond to this one, this green one, and this one is again. So, for this case, so for 1 cases, this is for 1 cases, okay, state 1 cases, for which cases we are going to the next state, okay, d value next state. So, clearly whenever 0 cases we are not going to the same cases, we are going to, for these cases, for 0 cases we are going to state A, for rest of the cases 1 cases we are going to the again same state, 10 cases same state, and 11 case also we are going to the same state. So, that means, so clearly, so this is q is equal to 1, red q x plus y, this red part it shows, and this green part already saying, and this thing is already covered here. So, next state output logic D will be x y plus q into x plus y. So, this will be the next state logic, and what will be the output logic or Z logic. So, at what point S is equal to 1. So, if you look at this thing, so state 0 and 1 0 and 0 1. So, this is state 0 and these 2 cases. So, these 2 cases. So, ultimately, so this correspond to, so this is you are in state 0 and x or y. So, these 2 cases, for these cases this S is equal to 1, and whenever in state 1, which cases it result a S is equal to 1. So, 1 and 0 cases, this is x NOR case. So, you are in state 0, then x or y will result a S is equal to 1. If you are in state 1, that means T 1, then x NOR 0 cases and 1 case, it will result a output S is equal to 1. Okay, this how we can implement. This is similar to FSM implementation, but what we are looking here is actually, so we do not do tabulations for a whole thing. So, the whole thing we are able to see this thing, these things were repenting in T 0 and this whole thing were repenting in T 1. So, we are looking at on which state you are and what are the input, based on that we are trying to do. Okay. So, this is a slightly different way of implementing the same thing. Okay. And ultimately how it looks like, the next state logic, this one it goes to here. So, D is equal to x y plus q x plus y, and Z logic is this one. So, S is equal to T 0 plus x or y plus T 1 into x NOR y. So, this thing goes to these places, and in this way we can implement serial binary adder. So, we model the things using FSM, then converted the model into ASM, and then we have implemented the ASM. So, in this case both FSM implementations and ASM implementations both looks almost similar. Okay. But what we are doing changes in this case, looking at the states based on input, what output we are getting, that we are looking at. Okay. So, we are not enumerating all the things, but only for the one cases we are looking at. Okay. So, that is the difference, almost similar, but slightly it is easier way to do the things. So, and let us look at another examples. So, in this example we will try to generate the external behavior also. External behavior means how from outside it look like. So, the full adder example is very small examples. This example is a little bit bigger example as compared to the full adder. So, let us design a circuit, digital circuits to sum first n odd numbers. So, if we do first n odd numbers, then clearly we can do with suppose 1 plus 3 plus 5 plus 7 into 2 n minus 1. So, this result is n square. Okay. So, but we want to use basic method in this case. So, we are not doing n square, we are not doing n square one. So, we are doing something means a very basic one. So, we will use basically the summation method. So, we will sum 1, 3, 5, 7 up to 2 n minus 1. So, let us draw the design FSM for this. So, initially similar to the ASM sum of first n odd numbers. So, initially when go is equal to 0. So, from go is equal to 0 means we want to design a circuit. So, once the go signal is given, then only it should start the computations, otherwise it will be in ideal. So, if g is equal to 0, it will stay in ideal state, okay, that means ready states, and when go is equal to 1, then it will initialize the thing, and once it is initialized, then it will start doing the computations, and till how much time it will do computations. So, because for n numbers, okay. So, initially we will provide n, then we will decrement that counter, and once it reaches 0, then it's come to the ideal state and it says that done, once already computed. So, this is the FSM for what I can say this problem. So, sum of first n odd numbers, and G and Z, these are the input, G and Z, this is the FSM. Whenever we are saying who is doing computations, the data path is doing computations, okay. In this case data path is doing computations. G we are giving from the outside, Z is equal to 0. So, whenever a decrementing counter, so the counter will generate when it reaches 0, okay. That means Z is a status input to the FSM from the data path. So, this is the FSM. So, this is the FSM and this is the ASM for that, and if you look at, there are clearly 3 states, okay. So, 3 states, A is equal to in this case 3 state 0 0 0 1 and 1 0, and this is state whenever G is equal to 0, it is stay in ideal state, and whenever G is equal to 1, this is init state, initialize, and this is compute 1, okay. And whenever means in compute state, it every time it decrement the counter, whenever it reaches 0, then it goes to the ideal state. This is done, kind of done, okay. So, this is the very high level ASM, okay. But for these examples we can represent the same thing. This one is actually more FSM. We can design the same problem with actually melee FSM, and it can be done with 2 states very easily. And if you convert this melee FSM, redesign melee FSM to the ASM, then we can manage the 2 states. And if you look at this thing, this is the The same problem with Mealy FSM modeling and alternate FSM with only 2 state is given here. So, in this case also this is ideal states, this is ideal state, and whenever g is equal to 1 we are doing initializations. Whenever g is equal to 1 we are doing initializations. In Moore FSM whenever g is equal to 1 it goes to another state and in that state it do initializations. But in this case in ideal state if g is equal to 1 it will do a actions. This is the conditional state box. Because this is conditional state box it can act as another states and you can do some set of actions based on the conditions. Okay. Because of that reasons we are able to model with Mealy FSM and it will result with lesser number of states. Okay. So, when g is equal to 1 it will initialize c is equal to 1, s is equal to 0 and p is equal to n. So, p means we are having a counter, decrementing counter, initially it will be loaded with n initial values, s is equal to summations and c is how many time we are counting, and after that every cycle, next every cycles what we are doing. So, this is another block, this one is another block. So, this example have 2 blocks, 2 ASM block. So, this ASM has 2 blocks, this is one block, this one is one block. So, state, condition box and all associated edges and its conditional boxes, and this is second ASM block. This is S0 state 0 and this is state 1. There are 2 states S0 and S1, 2 ASM blocks, and in this case what we are doing. So, in every cycle S is equal to S plus C we are doing. So, this is again we are using error. So, S is equal to S plus C, these RTL kind of statements, register transfer level statement. C is equal to C plus 2, this is also RTL kind of statement. S is equal to S plus C, this is C is equal to C plus 2 and P is equal to P minus 1. So, these are register transfer RTL level statement, RTL kind of statements, and from this we can infer. So, what should be our data path? So, clearly we are doing 2 additions and 1 subtractions. So, crudely we can say 2 adder and 1 decrementer or counter with decrement operations is more than enough. So, this example of 2 ASM blocks. So, clearly this is one block shown in red and this is another block. These are 2 ASM blocks. So, ASM block means it executes in one cycle. So, whole thing executes in one cycle. This is suppose state 0 and state 1. So, whenever you are in state 0, that means at the end of the cycle, so it execute all the things, all the action written in states, then conditions and conditional state box, all the 3 things executes together. And clearly in this case, because we require 2 adder 1 and 2, 2 adder, decrement register, this is decrementer 1, and clearly what is 2 register, S register we require, C register we require. Okay, and 2 constant. So, clearly this is constant, this is constant, okay, and this is again loading, and this is input, and it's input from the external world, and what is the output? S is the output from the external world. And whenever we are doing these things, so from external world what we want? So, G external input is G and go, and what is external output? External output is maybe one can say done and S. So, whether it is done or not, and final summations. So, external input is G and N, go and N, and external output is done, and S, what is the summations. These two things are external input and output. And what is the status? Status is whenever I are doing these operations, P is equal to P minus 1, it will generate an Z value. So, particularly these things. So, P is equal to P minus 1, it may result a 0. So, whenever its P is equal to 0, then this Z value will be 1, and whenever Z value will be 1, then it says it is done, and when it is done, then S value will be transferred to output port. Okay. So, this is the ASM of means this example sum of first and odd numbers. And what will be the data path? So, clearly are you able to see this thing? So, there are two adders, decrement register, S register and C register. This is the data path, and clearly what we are saying, S register, C register, this is decrement register, and two adders, adder 1, adder 2, and two constant, these are two constants as 1 and 2. This is the, and initially we are using two signals, one is clear signals, clear signal, it will clear both S and C equal to 0. Okay. Then LSC, what is LSC? LSC means load value to S and C. LSC, clear means it will clear, load means it will load. So, clear means it make it 0, okay, and load means it will load a particular values. Okay. So, in our earlier case if we look at, so C you are loading 1. So, S we are loading 0, C you are loading 1. So, in our examples what we require? So, C is equal to 1 we require, we need to load 1 to C, and S is equal to 0. This is in case of load we can do LSC, load S and C. Okay. And if you clear, whenever you are clear make it C is equal to 0 and S is equal to 0. But in our case we require both. Whenever it is in ideal state, it should do C is equal to 0 and S is equal to 0. Whenever it is doing the computation, starting the computations, okay. So, whenever go is equal to 1, it should load, okay, it should load. So, that is why we require both clear and load signals, okay, LSC, and this load is for loading counter value. So, particularly n value to P, okay. And what are the other signals? Other signal means every time we need to do decrement signals and 0 detects. So, whenever you are decrementing, it will give output whether it found is 0 or not, and we are not giving any signal to adder. Why? Because adder is a combinational component. Adder is a combinational component, and combinational component do not require any signal. Whatever the it give input, it will do the computations. For register we require load signals, for counter we require load signal. These are actually sequential component, but adder is not a sequential component, it is a combinational component. Whenever combinational component comes, we do not require any load signals or any signals, it will do automatically. Okay. So, this is data path of sum of first n odd numbers, and sum of first n numbers, looking at the what I can say this particularly looking at this ASM. So, we need to, similar to earlier case, we need to what implement this, we need to generate the all output, we need to generate all output next state. So, there are two states clearly, we need to generate states next state logic, okay. And there are two states, there is one D flip flop is sufficient and Z logic, output logic. And what are the things we need to generate? So, we need to generate clear, we need to generate load, we need to generate load S and C, okay, and decrement, done and ideal. and clearly from the ASM we can figure it out. So, when clear will be generated, when clear will be generated, just look at when clear will be generated. So, whenever G ideal state and G is equal to 1, clear and load will be generated. So, clearly clear and load will be generated in this case. First initially clear it and then load it. Okay. Then load SC, whenever you are in T1. So, you are in T1. So, load SC will be generated. So, load value from the other things. Okay, other things means in this case. So, unless it is loaded. Okay, so this load SC will be enabled. This value will not enter to the. Are you able to see this thing? So, unless this thing. So, this thing is value will be available here. Value will be available in the where. Value will be available in the where. But unless load is enabled, so this value will not enter to the register. So, value will not enter to the register unless it is loaded to SNC. And when we want to load every cycle, okay, whenever go is equal to 1, whenever you start the compression, at that time it need to be loaded, load an SNC. Okay. So, load NSG every cycle you need to load it. Load means this is T0 and G. So, whenever T0 is G, then load will be generated and clear will be generated. So, initially clear, then it will be loaded, and for every once compute cycle, whenever in T1 state, it will be loaded, then decremented, and once it is done, then it will be say output things are done, and it will go to the ideal state. And what is the ideal? If we are in state T0, then it is ideal state. Okay. So, ideal is T0, load SC every time, because register element are clocked elements and it is load enables. Unless you enable the load, it will not load. So, these two are, one is loading the initial values, this one is loading for initial values, and this one is loading for the currently calculated values. So, this one is for loading initial values, and this one is loading, this one is loading calculated value. Two things require. First thing is loading initial value, second one is loading calculated values. So, if you look at the diagrams, so this one is loading initial values. So, this correspond to LSC. So, this correspond to LSC, and this correspond to this is this correspond to LOAD, and this correspond to LSC. Unless it is done, it will not do. So, this is clear, and if you do this thing, so we can see this is load SC, every cycle, every compute cycle it will be once enabled, and clear it will have a mux, So, either it will load 1, or in this case whenever you are putting here, in this case it will be loaded with S is equal to 0, and this will be C is equal to 1. So, whenever clear in the first cycle, so clear it make it S is equal to 0 and C is equal to 1, and LSC it will do, in case of LSC it will take the older values. So, particularly this is computed value. So, we can say computed S and this is computed CC. So, in this case S will be computed S value and C equal to computed C values. So, this is LSC will do this work. This one is computed C value, this is computed S values. So, in this way means this will generate the what you can say, you can generate signals. Okay. So, this is our what you can say ASM. So, this is our ASM implementations and how ASM will interconnect with the data path. So, ASM interconnection with data path. So, this one is ASM implementations. So, ASM implementations are many output signals, also it takes input signal. What input signal it takes? It takes input signal G and Z. Okay. So, one is go, another is 0. So, this is the input signals. Okay. And what it generate? Clear, load, TSC, decrement, done and ideal. And now we need to connect both. This is the control path and this is the data path. So, we need to connect both the things. That means, this 0 need to get connected to 0. Okay. 0 need to get connected to this thing. Anyhow, go will come from outside. So, we do not require. Okay. And then this all signal need to get connected to the corresponding places. So, let us see and connect the thing. Oh, done. So, now this thing are getting connected. Okay. So, this thing, this is clear, clear is connected to clear, this is clear is connected to clear, then are able to see decrements, this is Z values, Z value is connected to Z values, this Z value is connected to Z values, go is coming from outside, go is coming from outside, then done. So, this one is done, done is going outsides, ideal is going outsides, okay. Ideal is going outsides, then decrement, from where we are getting decrement. So, from Z logic whether to decrement or not, this one is coming from these sides, okay. This is the data path, this one is data path, this is the clear signals. So, we are getting clear signals, this is the first one is load 1. So, this one is load 1, this is the load 1, then this is load SC, LSC it is getting connected to the LSC. So, in this way it is actually connecting both, this is data this is control path and this is data path, and from outside some will come from here some will come, okay. And what we are loading? Loading is n, we are loading n, getting some. So, we want to design a circuit which can calculate sum of first n order numbers. So, we require to supply n, then give the go signals, we will get done signals and resultant output. Okay. So, this is the complete both control path and data path. This makes the things complete. Okay. And how from the external it look like? So, from external what we are giving? We are giving go signals, okay, and we are giving n. So, these are the two inputs, go and n we are giving, and what we are getting? Either it is ideal, not doing anything. So, if we are not giving any go signal, then it will be ideal, otherwise it will be doing something. Done signals, this is the output, and what we are getting output final sum. So, this is interfacing with external world. This is the control path, this is the data path, and control and data path. So, both CP and DP, this constitute of digital system, and how will interact with the external world? This is actually we are giving go signal and this is the input, and these are the output, done, ideal and some are the output. This constitute the full digital system, sequential digital system design using RTL methodology or ASM methodology or FSMD methodology with a concrete example, summation of first and odd numbers. And in this way we can design many other circuits. So, in the next classes we will have many more examples, so which will have actually similar kind of design philosophy, so that your understanding will be much clearer. Okay. So, thank you. So, next class we will meet.